Welcome to Chapter 3 on the second and third laws of thermodynamics. Our central question is deceptively simple. Given that the first law permits a change because energy is conserved, will that change actually occur? The second law supplies direction through entropy, while the third law gives entropy an absolute reference at 0 Kelvin. We shall then concentrate on the chemical system by introducing Helmholtz and Gibbs energies, and finally combine the first and second laws to obtain several powerful property relations. These ideas are the foundation for chemical equilibrium, phase stability, and the phase diagrams that we shall encounter later. The first law tells us that energy is conserved, but conservation alone does not explain the arrow of change. A bouncing ball progressively loses organized mechanical energy to the microscopic thermal motion of the floor. The reverse event is not forbidden by energy conservation. In principle, atoms in the floor could move together and launch the ball, yet that would require an astronomically unlikely coordination of random molecular motion. Spontaneous change therefore tends to disperse energy and matter over the available microscopic possibilities. This statistical asymmetry between a few organized states and an enormous number of dispersed states is the molecular heart of irreversibility. We distinguish spontaneous processes, which have a natural direction under the stated conditions, from non-spontaneous processes, which require coupling to some other change. Kelvin's statement says that no cyclic device can take heat from a single reservoir and convert it completely into work. Some energy must be rejected or dispersed elsewhere. Clausius gives an equivalent statement. Heat does not spontaneously pass from a colder body to a hotter one. A refrigerator can certainly drive heat in that direction, but only by consuming work and producing an additional change in the surroundings. These are different faces of the same second law. This diagram isolates the Clausius argument. Imagine heat moving from the cold sink to the hot source with no work input and no other consequence. The first law would not object, because the amount of energy lost by one body equals the amount gained by the other. The second law does object. If an amount of heat Q leaves the cold body, its entropy falls by approximately Q divided by the lower temperature. The hot body gains only Q divided by the higher temperature, a smaller amount. Total entropy would decrease. The forbidden direction is therefore identified quantitatively by the sign of the total entropy change. Entropy, symbol S, lets us combine the many verbal forms of the second law into one criterion for any spontaneous change. The total entropy change of the system plus its surroundings is positive. At equilibrium, it is 0 for an infinitesimal allowed change. Notice that the criterion concerns the total, not necessarily the system alone. A liquid may freeze spontaneously below its freezing point even though the liquid to solid change lowers the system's entropy, because the released heat increases the entropy of the surroundings by a larger amount. Irreversible processes generate entropy. A perfectly reversible limiting process has 0 total entropy production. The thermodynamic definition is dS equals reversible heat divided by the absolute temperature. For a finite change, delta S is the integral from the initial to the final state of dQ reversible over T. The word reversible is essential. Entropy is a state function, so its change depends only on the end states, but heat is path dependent. We therefore invent any convenient reversible path connecting those states, even when the actual process is irreversible. At each small stage, we divide the reversibly supplied heat by the temperature at which it is transferred. Entropy has units of joules per Kelvin. Molar entropy has units of joules per Kelvin per mole. For the surroundings, the calculation is often especially simple because the surroundings are treated as a large thermal reservoir at nearly constant temperature. Their entropy change is Q surroundings divided by T surroundings, or equivalently minus Q system divided by T surroundings. In an adiabatic process, no heat crosses the system boundary, so the entropy change of the surroundings is zero. Do not conclude that the system entropy must also be zero. A reversible adiabatic change is isentropic, but an irreversible adiabatic change, such as free expansion of a gas, produces entropy within the system. Adiabatic means no heat transfer. Isentropic is a stronger condition. Boltzmann's statistical definition connects macroscopic entropy to molecular possibilities. S equals K times the natural logarithm of W. Here K is the Boltzmann constant and W is the number of microstates compatible with the specified macroscopic state. The logarithm is important because independent systems multiply their numbers of microstates, whereas their entropies must add. If exactly one microstate is accessible, W is 1 and the entropy is 0. As W increases, entropy increases. It is safer to think of entropy as the logarithmic measure of energy and matter dispersal than simply as disorder, because the microstate definition is precise and quantitative. The particle in a box picture gives a useful molecular example. When the box expands, its quantized energy levels move closer together. At the same total energy, more combinations of molecular energy levels become accessible. Consequently, W increases, and so does S. This explains why an ideal gas spreads spontaneously into a larger available volume. There is no mysterious force pushing it outward. The expanded macrostate corresponds to vastly more microstates than the confined macrostate. A random walk through molecular configurations therefore spends essentially all its time in the expanded state, while a spontaneous return of every molecule to the original small region is overwhelmingly improbable. Entropy is a state function, which means its cyclic integral is zero. If we take a system around any closed reversible path and return to the initial state, the integral of dq reversible over t vanishes. The textbook argument can be built in 3 stages. First, establish the result for a Carnot cycle, then show that a general reversible cycle can be tiled by many tiny Carnot cycles, and finally take the limiting case in which those cycles become infinitesimal. Internal boundaries cancel, leaving only the outer path. This state function property is what allows us to calculate entropy changes using convenient and hypothetical reversible routes. The pressure-volume path shown here may be irregular, but it returns to its starting state. Work and heat accumulated around such a cycle need not be zero, because they depend on the path. By contrast, the net change in every state function is zero. Delta U, delta H, delta S, and delta G all vanish over the complete cycle. Graphically, the final state after one circuit is thermodynamically identical to the initial state. This distinction between path functions and state functions is one of the most useful organizing ideas in thermodynamics. It allows Hess-type cycles and indirect calculations even when the direct process is experimentally inaccessible. For an ideal gas expanding isothermally from volume V initial to V final, a reversible path gives Q reversible equals nRT logarithm of V final over V initial. Dividing by T gives delta S system equals nR logarithm of that volume ratio. Expansion therefore raises the gas entropy. If the expansion is reversible, the surroundings lose exactly the same entropy and delta S total is zero. If the gas expands freely into a vacuum, Q and W are both zero and the temperature of an ideal gas is unchanged, yet the system has the same positive entropy change because the end states are identical. In that case, the total entropy change is positive. A phase transition changes the way matter is dispersed. At the transition temperature, where 2 phases coexist reversibly, the molar transition entropy is delta H transition divided by T transition. Vaporization has a large positive entropy change because a compact liquid becomes a widely dispersed gas. Fusion is also positive, though usually smaller. For exothermic reverse transitions such as condensation and freezing, the system entropy change is negative. At the exact equilibrium transition temperature, heat released to or absorbed from the surroundings supplies the opposite entropy change, so the total is zero. Away from equilibrium, the balance produces a positive total entropy change in the spontaneous direction. These tables illustrate the magnitudes involved. Fusion entropies depend strongly on molecular structure and on how much additional freedom the liquid gains relative to the solid. Vaporization entropies at normal boiling points are often surprisingly similar, commonly near 85 joules per Kelvin per mole for many non-associated liquids. This empirical regularity is Troughton's rule. Water is a notable exception because its liquid is strongly hydrogen bonded and unusually ordered, so vaporization releases more configurational freedom and gives a larger entropy change. Such deviations are chemically informative. Entropy data can reveal intermolecular structure, not merely provide bookkeeping numbers. For heating without a phase change, dq reversible at constant pressure is Cp dt. Therefore the entropy change is the integral of Cp over T dt. If the heat capacity is approximately constant over the interval, delta S equals Cp times the natural logarithm of T final over T initial. Because of the 1 over T factor, supplying the same amount of heat at a lower temperature produces a larger entropy increase than supplying it at a higher temperature. If heating crosses a phase transition, we integrate within each phase and add the transition entropy, delta H transition over T transition, at every boundary. Absolute entropy is assembled calorimetrically from 0 Kelvin upward. We integrate the appropriate heat capacity divided by temperature through each stable phase and add each transition enthalpy divided by its transition temperature. Thus the molar entropy at the final temperature contains the low temperature solid contribution, the entropy of fusion, the liquid heating contribution, the entropy of vaporization if relevant, and the gas heating contribution. The only quantity not supplied directly by these measurements is S at 0 Kelvin. The third law provides that reference, subject to the requirement of a perfectly ordered crystal. As temperature approaches absolute zero, thermal excitation is quenched. In a perfect crystal, all particles occupy a unique, regular arrangement and the ground state is the only accessible microstate. Boltzmann's formula then gives S equals K logarithm 1, which is 0. The adjective perfect matters. If a solid retains orientational disorder, mixed site occupancy, defects, or glassy disorder at 0 Kelvin, more than one arrangement may remain accessible in principle. Such a material has residual entropy. The simple zero entropy statement applies to a pure, perfectly crystalline, perfectly ordered substance. The Nernst heat theorem states that the entropy change accompanying any physical or chemical transformation approaches zero as temperature approaches zero, provided every substance involved is perfectly ordered. This means that the entropy curves of alternative perfectly ordered states converge at 0 Kelvin. One consequence is that heat capacities must tend towards zero at low temperature strongly enough for the integral of Cp over T to remain finite. The theorem also explains why absolute zero cannot be reached by a finite sequence of ordinary cooling operations. Thermodynamic changes become progressively less effective as the temperature approaches zero. The third law assigns zero entropy to every perfect crystalline substance at 0 Kelvin. This is stronger than the convention used for standard enthalpies of formation, where elements are assigned zero by definition at a chosen temperature. Third law entropy has a physically motivated absolute zero. Once that origin is established, calorimetry gives absolute molar entropies at higher temperatures. Again, defects and frozen disorder can produce residual entropy, so experimental samples may require a correction. Absolute entropy is enormously useful because reaction entropies can then be calculated directly from tabulated molar values. Third law entropies are denoted as standard when the substance is in its standard state. The standard reaction entropy is the stoichiometric sum of standard molar entropies of products minus that of reactants, sum over nu Js standard J. Stoichiometric coefficients carry their algebraic signs, or equivalently, products and reactants may be written as separate sums. For ions in aqueous solution, an additional convention is needed because single ion quantities cannot be measured independently. The standard entropy of the aqueous hydrogen ion is assigned 0, allowing a consistent table of other ionic entropies. The table reveals several broad trends. Gases have much larger molar entropies than liquids or solids because translational motion through a large volume creates many accessible microstates. More complex and heavier molecules often have larger entropies because they possess more rotational and vibrational modes. Even two solid forms of carbon differ. Graphite has a larger standard entropy than diamond because their lattice structures and vibrational spectra are different. These are absolute entropies, so values are generally not 0 at room temperature, even for elements in their standard states. Do not confuse standard entropy with standard enthalpy of formation. We now replace the system plus surroundings criterion with functions of the system alone. Start from the Clausius inequality. ds is greater than or equal to dq over T. At constant volume, with only pressure volume work, dqv equals du. Therefore Tds is greater than or equal to du, or du minus Tds is less than or equal to 0. At constant internal energy, spontaneous change increases entropy. At constant entropy, spontaneous change decreases internal energy. These equivalent views motivate a new state function suited to constant temperature and volume, the Helmholtz energy. At constant pressure, and when expansion work is the only work, heat supplied equals the enthalpy change. The Clausius inequality then gives Tds greater than or equal to dH. Thus, at constant enthalpy, the spontaneous change increases entropy, whereas at constant entropy it decreases enthalpy. Most laboratory chemistry occurs under approximately constant pressure and temperature, but neither the system entropy nor enthalpy alone gives a universal direction criterion under those conditions. Their combination, H-Ts, does. That combination is the Gibbs energy, the most widely used potential in chemical thermodynamics. The Helmholtz energy is A equals U minus Ts. The Gibbs energy is G equals H minus Ts. At constant temperature, their differentials are dE equals du minus Tds and dG equals dH minus Tds. These definitions combine an energetic tendency towards lower U or H with an entropic tendency towards larger S. The factor T controls the importance of entropy. At low temperature, enthalpic effects often dominate, while at higher temperature an entropy advantage can overturn them. Which potential is appropriate depends on the experimental constraints, not on personal preference. The resulting spontaneity criteria are compact. At constant temperature and volume, a spontaneous change has d less than 0. Equilibrium corresponds to a minimum of A. At constant temperature and pressure, dG is less than 0. Equilibrium corresponds to a minimum of G. Helmholtz energy also has a direct work interpretation. At constant temperature, the decrease in A gives the maximum work obtainable from a process, including expansion work. The actual work is smaller when the process is irreversible. These minimum principles are powerful because they refer only to properties of the system. Gibbs energy is especially important in chemistry because reactions and phase changes are commonly studied at fixed temperature and pressure. A reaction is spontaneous in the direction that lowers G. If dG is positive in the forward direction, the reverse direction is spontaneous. At equilibrium, dG is 0 for an infinitesimal permitted advancement, and G is at a minimum with respect to the reaction or phase composition coordinate. This criterion underlies chemical equilibrium constants and phase diagrams. Coexisting phases are stable when transferring a small amount of material between them cannot lower the total Gibbs energy. Standard enthalpies and entropies combine to give the standard reaction Gibbs energy. Delta Rg standard equals delta Rh standard minus T delta Rs standard. Alternatively, use tabulated standard Gibbs energies of formation. The reaction value is the stoichiometric sum for products minus the corresponding sum for reactants. A negative standard reaction Gibbs energy means products are favored relative to reactants when every species is in its standard state. It does not by itself guarantee a fast reaction, because thermodynamics addresses direction and equilibrium, whereas kinetics addresses rate and activation barriers. Here are representative standard Gibbs energies of formation at 298 Kelvin. Elements in their reference states have 0 by convention, but alternative allotropes need not. Diamond, for example, lies slightly above graphite in Gibbs energy under standard conditions. Strongly negative values, such as those for water, carbon dioxide, and sodium chloride, indicate substantial thermodynamic stabilization relative to the constituent elements. For aqueous ions, individual formation values require the convention that the standard Gibbs energy of formation of the aqueous hydrogen ion is 0. Reaction values calculated from the table remain physically measurable and convention independent. These thermodynamic cycles determine single ion solvation quantities using measurable combinations and a stated ionic convention. Because Gibbs energy is a state function, the sum around each closed cycle is 0. We can combine atomization, ionization, electron attachment, molecular dissociation, and solvation steps to infer an unknown aqueous ion formation value. Chloride and iodide differ because the gas phase energetics and hydration strengths differ. The smaller chloride ion is generally hydrated more strongly than iodide. The method is a Gibbs energy analog of a Born-Haber cycle and illustrates how state functions turn inaccessible transformations into calculable ones. Combining the first and second laws gives the fundamental equation for a closed system of fixed composition doing only pressure-volume work. du equals Tds minus Pdv. If U is regarded as a function of its natural variables S and V, comparison with the total differential identifies temperature as the partial derivative of U with respect to S at constant V, and pressure as minus the partial derivative of U with respect to V at constant S. Temperature and pressure are therefore not merely empirical readings, they emerge as slopes of the fundamental energy surface. Because thermodynamic potentials are state functions with exact differentials, their mixed second derivatives are equal. This produces the Maxwell relations. From du equals Tds minus Pdv, for example, the derivative of temperature with respect to volume at constant entropy equals minus the derivative of pressure with respect to entropy at constant volume. The table gives analogous relations derived from H, A, and G. Their practical value is that a difficult-to-measure entropy derivative can be replaced by a pressure, volume, or temperature derivative that is experimentally accessible. They are mathematical bridges between thermal and mechanical properties. For Gibbs energy, the fundamental differential at fixed composition is dG equals VdP minus SdT. Its natural variables are therefore temperature and pressure. Direct comparison gives the partial derivative of G with respect to temperature at constant pressure as minus S, and the partial derivative with respect to pressure at constant temperature as V. Hence Gibbs energy decreases with temperature because entropy is positive, and it increases with pressure because volume is positive. The size of each slope has physical meaning. These relations also provide the local geometry underlying phase equilibrium and the pressure-temperature phase diagram. Temperature dependence may be rearranged into the Gibbs-Helmholtz equation. The derivative of G over T with respect to T at constant pressure is minus H over T squared. Applied to a reaction, the same equation relates the temperature variation of delta Rg over T to delta Rh. Through the connection between Gibbs energy and the equilibrium constant, it leads to the Van 't Hoff equation. Thus, reaction enthalpy predicts how equilibrium shifts with temperature. Heating favors the endothermic direction, while cooling favors the exothermic direction, provided the enthalpy does not vary too strongly. Finally, consider pressure. Since the derivative of molar Gibbs energy with respect to pressure is molar volume, integration gives its pressure dependence. For an incompressible solid or liquid, the molar volume is nearly constant, so Gm at pressure P is approximately Gm at a reference pressure plus Vm times the pressure difference. For an ideal gas, Vm equals RT over P, and integration gives Gm equals Gm standard plus RT logarithm of P over standard pressure. This logarithmic pressure term becomes the basis of gas chemical potential, reaction quotients, equilibrium constants, and ultimately the construction of phase equilibria. That completes our development of the second and third laws and their principal chemical energy functions.